Hello everyone, this is the first of a series of videos dedicated to nuclear magnetic resonance spectroscopy. Over these videos we will be looking at the scientific basis of NMR spectroscopy, and we will also look at how an NMR spectrometer works. We will discuss the strengths and limitations of NMR spectroscopy. We will also spend most of the time learning how to interpret NMR spectra of simple molecules, specifically proton and carbon-13 NMR. And when I say simple, I don't mean they are easy to interpret. What I mean is that they are discrete, small molecules. They are not macromolecules, such as, for example, proteins. We will look at NMR of proteins in future years. We looked at the electromagnetic spectrum when we were discussing infrared spectroscopy. For the case of NMR, the section that we are using from the electromagnetic spectrum is the area with the lower frequency and the longer wavelengths, the radio frequencies of the spectrum. And those radio frequencies, those particular wavelengths, will elicit nuclear spin transitions, which is the basis of NMR. You're probably familiar with a medical application of nuclear magnetic resonance spectroscopy, and it's magnetic resonance imaging, MRI. MRI looks at the internal structure of the body. In MRI, the magnet has the strength of 1 to 3 Tesla. It's a superconducting magnet, and the magnetic field that magnet produces is 50,000 times stronger than the Earth's magnetic field. When we use an NMR, we are looking at the structure of the molecules. A typical NMR is 600 megahertz. It produces a magnetic field that is 2,035,000 times stronger than the Earth magnetic field. So it's a very, very powerful magnet. The core needs to be kept at very cold temperatures, minus 270 degrees. And to do that, we use helium, liquid helium. So a bit about the basics of how NMR spectroscopy works. When a charged particle, when a proton spins on its axis, it creates a small magnetic field. So you can think of a nucleus as a tiny bar magnet. Typically, in absence of a magnetic field, those tiny bar magnets will be oriented randomly in space. When they are in the presence of magnetic field, they will align with respect to that magnetic field. They might align along parallel to the field or anti-parallel to the field. So they will be aligned oriented with or against the external magnetic field. More nuclei will be oriented parallel to the magnetic field because it's the lower energy state. And the energy difference between those two states, the with or against the magnetic field, that parallel and anti-parallel conditions, is very small. So if we imagine our nucleus, our tiny bar magnet, exposed to a magnetic field, an external magnetic field, and we imagine one of those nuclei which is parallel to the field, it is in a lower energy state. The anti-parallel against the magnetic field will be, those nuclei will be in a higher energy state. Applying the right amount of energy is you are able to move up a nucleus which is in a parallel position, aligned to the magnetic field, into an anti-parallel one against the magnetic field. That's an unstable state, and the nucleus suffers a process of relaxation. It goes back to the parallel with the magnetic field state, which is lower energy and is more stable. We call that effect, this relaxation process, resonance. So what we do when we are doing NMR spectroscopy is we apply radio waves. We apply a radio wave to the system, and we make the nuclei to flip from being in the low energy state, parallel to the magnetic field, to an anti-parallel high energy state. The nuclei will flip back, what we call relaxation process, to their low energy state, and they will give off radio waves. And that energy, those radio waves that give off, depend on the nucleus and it depends on the chemical and magnetic environment in which that nucleus is. So what do you detect in a NMR spectrum? Well, in a proton NMR spectrum, hydrogen NMR spectrum, we detect hydrogen atoms in different environments. Those hydrogens, the nuclei of those hydrogens, will absorb different amounts of energy, different radio waves, and depending on their environment, depending on what's surrounding them. And they will experience different magnetic fields, and that's what you detect in an NMR spectrometer. We compare any signal from any hydrogen, any nucleus, but in this case hydrogen, to a standard. And the standard we choose is TMS, tetramethylsilane. And this is a structure of tetramethylsilane. It's a silicon atom attached to 4 methyl groups. And we use that as a comparison, and that sets the 0 in the scale. So you've got here in this slide a typical proton NMR spectrum, in this case for the compound methyl acetate. And as you can see, it has 2 peaks, well, 3 peaks. One of them is the peak at 0, and I will tell you what that means. ppm means parts per million, and what we measure in the x-axis is something called chemical shift, and I will talk about chemical shift. Signal is called delta. We use the letter delta to call it, and in the y-axis is the intensity of the signal. So the signal at 0 is the standard, is the TMS, is the tetramethylsilane. And it's because the rest of the spectrum is going to be a scale with respect to that 0. So we define TMS as the peak that appears as 0. We have 2 other peaks, one green and one purple in the slide. And what does that mean? It means that we have hydrogens in 2 different environments. And in this case, it's reflecting this, the hydrogens that is attached to this methyl group that are next to the oxygen in the ester bond, and the hydrogens in this methyl group that is directly attached to the carbon with the carbonyl group. So those are hydrogens in 2 different environments, and that's what we detect, 2 peaks. And they appear in different places in the spectrum because they react different to the magnetic field, and they absorb different amounts of energy, radio waves, and they give a different signal. And we measure that difference, where that position in the spectrum, we call that chemical shift. And chemical shifts are measured in something in parts per million. This is a table of some typical chemical shifts for proton NMR. So we've got here at 0, by definition, the reference, tetramethylsilane, and then we have where different hydrogens belonging to different groups appear. So you can see that some of them, for example, this is an alkyl group, hydrogens in a structure that only has single bonds, and 3 hydrogens. And if you compare that with an alkyl, but in which you don't have 3 hydrogens, not a terminal alkyl group, but a secondary alkyl group, an alkyl group that is in between 2 carbons, you see that the chemical shift is different because those hydrogens are in different environments. It's different for those hydrogens, for hydrogens to be at the end of a chain, in a carbon at the end of the chain, that they are hydrogens in the middle of a chain, in the chain, in between 2 carbons. And again, that is slightly different to have a hydrogen, a tertiary alkyl, a hydrogen that is attached to a carbon that is surrounded by 3 other carbons. So as you can see, what those hydrogens are attached to determines the position in the NMR spectrum, the position in which those peaks corresponding to those hydrogens would appear in the NMR spectrum.